All right, so our second paper this morning is zero. We'll talk about extreme changes in changes. Thank you. Take it away.
Thank you for inviting me to the conference. I like the format of the conference. It's challenging to present someone as paper where the person is sitting there. So I hope I can do a good job there, Yeah. So this paper is about extreme changes and changes. So before we talk about extreme changes and changes, I will introduce you to changes and changes first, and then we go to the extreme. Okay. So you are all familiar with the different models, and it's popular in economics and social sciences. So it relies on two assumptions: the parallel trend assumption and the no anticipation assumption. So under these two assumptions, the different estimate would identify the average effect on the treated group. But sometimes, if you think about that, the context where people use definitive, it's a context where usually people they have some targets part of the population. Like if you think about minimum wage, right? People for whom the wage is not binding. If you increase the minimum wage, they will not be affected. But you use definitive, you get the average effect of that policy on the whole distribution. Okay, and you may not find any effect because you are looking at the whole distribution, and most people who are targeted by that policy, there are only few of them in the population. So you probably want to zoom in and look at people around the minimum wage and see if there is any improvement in their wage or their employment. So in that case, if you just use the simple definitive, you will miss that. Okay. So another example that the authors gave in the paper is when people want to look at the effect on low birth weight. So sometimes they focus on kids with babies with low birth, and they want to design some policy to kind of improve the weight of these kids. But then if you look at the average effect on the whole population of babies, then you don't see anything because you're just looking at the average, and most people they don't have low birth weight. So this paper is kind of proposing a way to look at targeted part of the distribution instead of the whole population. Okay. So one solution to that is the standard definitive, but then in distribution. You can just use the standard definitive, but then look at the distribution. But then this works under very restrictive assumptions I will show you. And Robin Santana, they show in a recent paper in Economica that if you are using the definitive at the distribution level, you are either making the assumption that the treatment is going to be assigned, or you are making the assumption that the distribution of the counterfactual outcome is not changing over time within each treatment arm, or a mixture of the two. Which means that it's in these very special cases that you can have the assumption, the definitive assumption holds at the distribution level. So it's very restrictive in that sense. Then there is a method proposed by AT&T since 2006. But it's not popular. I don't know why people don't use that very often. Maybe because they don't have a data code. So the good news here is there will be a data code at the end of this talk. So they allow for non-random assignment, and they also allow for heterogeneity across time. So what the method does is basically they propose a way to estimate the quantile treatment effect, but then it works for quantiles that are in intermediate, like if you have 5% to 95%. So the current paper is proposing a way, if you think about the low birth weight, if there are like 2.5% of them in the population, then you cannot use, if you are using the method by eating events, then you will not identify the effect for these people, or you will wrongly estimate that. So this method that they are proposing, they will, if you are looking at people at 1% population, 1 percentile, 2 percentile, or less than 5 percentile, you will actually be able to implement that. And I think it's a great contribution in that sense. Okay, so yes, as I was saying, sometimes if you think about policies, usually, they kind of usually create some discontinuity in the outcome variable. For example, when you increase the minimum wage, sometimes it creates some spike at the minimum wage. First, they may comply with the law and then raise the wage for people. And that creates some discontinuity in that. So that also creates some challenges in terms of how you identify the effect when the distribution has some bunching or discontinuity. So I think the paper that's here is kind of looking at an interesting question, and it's for me, it's of personal interest. So let's discuss the main contribution of the paper. So whether if you are the lower tail of the distribution, like less than 5%, or you are the upper tail of the distribution, like more than 95%, this paper kind of proposes a way to estimate the distributional treatment effect, or the quantile version of the treatment effect. Okay? And what I think is interesting, the estimator, I look at it, it's like, oh, where did they get this estimator from? And it seems like it's asymptotically normal, even though the rate of convergence is not the same, the usual root N convergence rate, but the distribution is asymptotically normal. Sorry. So, and they have some practical guidance how to decide whether 5% is at the lower tail of the distribution or 7%. So they have a way to check that. I think that's really cool, because you in practice, you don't know whether the people that you are looking at are really at the lower tail or the upper tail of the distribution. How you can know that? They propose a practical way of doing that. And so they show that if you have the intermediate quantile, use AT&E based approach. And if you have the extreme one, use the approach. So it's like a combination. You can use a combination for some, and I will show in the application. When you are at the intermediate level, you show nicely that AT&E based approach works. But if you are at the extreme, then you will show that the approach works very well. Okay. So, and then they have an application, always that, right? If you want people to use your method, you need an application. So what they look at is, they look at the effect of earned income tax credit, okay, that provides some additional cash to people who qualify, and they want to see this new cash that they have, does that help them feed themselves better and then increase the weight of the newborns? So basically that's what they try to investigate here. They're going to look at quantiles less than 5% and see if there's any effect there. And if you just naively implement the approach using AT&E based, you may see your estimate may be biased. Okay. And most importantly, and I think this is good for, since Stata is financing this conference, so they provide this data package, and you can use that, you can implement that, and I think it's easily available. You just run tap the code, and then you get the results. And I will show you the nice graph that they proposed. So this is the main contribution of the paper. But I'm going to introduce you to the model and the assumptions, and when you can actually use this method. Okay. So this is basically the standard diff and diff framework, right? So you have the outcome in period T, okay, the observed outcome in period T, YT. And then we can write it as a potential outcome framework, okay? So you have the YT of 1 is the potential outcome for the treated group. And then YT of 0 is the potential outcome for the untreated group. Okay, and then the treatment happens between period 0 and 1, okay? So then they have a structural model for the potential outcome. So that structural model here is like a function of time, right? And also the potential treatment, okay, the treatment arm, and then there's unobserved heterogeneity. And one restriction here is that unobserved heterogeneity is a scalar, okay? It cannot be a vector. So that's the first restriction of the paper. So this unobserved heterogeneity in the structural equation is a scalar. So if it's a vector, then the changes will not work, okay? So now, under that, you need 3 assumptions to be able to identify the quantile treatment effect. The first one is the time invariance assumption. The distribution of this unobserved heterogeneity within each treatment arm is constant across time, is the same across time, okay? So if you think about the diff and diff setting, there is always an assumption about something that is stable over time, okay? In the standard diff and diff, It's like the selection bias, which is the difference that you see between the treatment and control group before the treatment happens, is stable over time. In synthetic control is the weight that you get in the pre-treatment period, right? For people in the donor pool, that weight is stable over time. So here, this distribution of the unobserved heterogeneity is assumed to be stable over time within each treatment arm, okay? And then you have an assumption called the monotonicity and continuity. So the H function is continuous and strictly increasing in this unobserved heterogeneity. So it's important in order to kind of invert the function and get the distribution of the unobserved heterogeneity in period 0, and then kind of transfer that to the period 1. That's how you achieve identification. And then there is one last condition, which is kind of support condition. So the distribution of the unobserved heterogeneity within the treatment group, okay, is included of the distribution in the distribution of the support of the unobserved heterogeneity within the treatment group is included in the support of the same unobserved heterogeneity within the control group. So if you have a policy, for example, that is expanding the support of this unobserved heterogeneity, then you cannot use the changes in changes. So it doesn't have a testable implication, but then you need to kind of discuss whether you believe that these assumptions hold, okay? So what if we just use the standard, okay, distributional DID, okay? This here is kind of the parallel trend, okay, at the distribution level. So you look at the difference between the untreated potential outcome in period 1 and then within the treatment group, right? This difference for the treatment group, and then you compare that to the same difference for the control group. So at the expectation level, that's kind of what you call parallel trend. But at the distributional level, that's what you get. And that has to hold for any value of the outcome, okay? So it has a testable implication because when you look at what you are looking for is the red distribution here. You can back out that from this equation, you just pass the other one on the other side. Then you get this counterfactual distribution that you're looking for. But nothing guarantees that if you take this function here plus this difference, it will always be a distribution. It may not be monotone, right? So if you see that in the data that this quantity, this function here is not monotone, it means that the parallel trend at the distribution level is rejected. And in most cases, it will be rejected in the applications. Usually it's rejected because it is strong assumption. As I was saying in the beginning, it holds either under random assignment or under time homogeneity that the distribution of the untreated potential outcome is not changing over time within each treatment arm. So because it is strong assumption, the changes appear to be a natural way because it makes some assumptions that, okay, it relies on the stability assumption that the distribution of the unobserved heterogeneity is not changing over time. But then also, at the same time, if you think about production functions, people kind of have the structure and sometimes they're willing to make these kind of assumptions, saying, okay, this is kind of my production function. And even though I don't know the unobserved heterogeneity, I'm going to assume that the distribution is stable. You don't have to know the distribution per se, right? It's just that it's stable, and that's enough to achieve point identification. So let me give you an example about what restrictions this assumption impose on the DGP, okay? So I'm kind of trying to be selfish here, and then I'm taking an example from a paper of mine with some quarters. So let's look at the period 0. Okay, assume that in the period 0, your Y0 is just equal to this unobserved heterogeneity, U0. And then in period 1, the Y1 is just equal to the treatment effect, which is the eta here, times the treatment status, plus this unobserved heterogeneity in period 1, U1. So then the treatment is such that people self-select on the gain. So kind of, for example, think about people are kind of, they have perfect foresight, so they know exactly what the gain will be. This is a restrictive example. So they self-select based on the gain. Like if you think about education, going to college, assume that you know exactly what the return will be, and you see if the return is positive, then you decide to go. If it's negative, you don't go. So that's kind of the framework here. So it's called the raw selection model. So we have the fully parametric model where everything is normally distributed. We know if we identify the parameters, then we characterize the whole distribution of the counterfactual outcomes. So the parallel trend assumption, right, the standard one would kind of here assume that the covariance between the gain here and the U0 is the same as the covariance between the gain and the U1. So that covariance is stable over time, okay? In other words, it's like the selection bias, which is here is kind of captured by the correlation, the dependence between the eta here and the U1. And also the dependence between the eta and the U0 is kind of stable over time. So if you think about the parameters, it's saying that the rho 0 times sigma 0 is the same as the rho 1 times sigma 1, okay? But then if you look at the distribution of DID, it's saying that the rho 0 is equal to rho 1 and the sigma 1 square is equal to sigma 0 square, which is kind of, once you know that, right, you know this part of the distribution, then you know exactly the counterfactual distribution that you are looking for. So if you are imposing the distribution parallel trend assumption, it's like you are assuming what you want to show, basically. So you are, as by assumption, your model, what you want to identify, holds by assumption. So it's very restrictive. But if you look at the changes assumption by eating event, it's just saying that the correlation in period 0 between the eta, right, the eta, which is the gain, and the U0 is the same as the correlation between the eta and the U1. Basically, the dependent structure, right, between the U0 and the gain is stable over time. So you only need to assume that that dependence is stable over time. You don't impose any restriction on the modular distributions per se, which the distributional diff does. Right. So in that sense, in some cases, yes, it makes sense to make just the assumption about the stability. You need that in diff setting anyway, right? You need something to be stable. So it's like the dependent structure between the treatment and the potential outcome is stable over time. You don't need anything more than that. Okay? So under that, basically, you point to identify the counterfactual distribution that you are looking for. So which gives you a way to kind of look at any quantile, 1%, 2%, 90%, 99%, which is gives more, as I was saying in the beginning, if you look at minimum wage and you look at the average effect, you may not see anything, but if you zoom in and look at people at the bottom of the distribution, there may be 1%, 2%, then you can see the effect. So this gives you actually the point identification of the distribution. The intuition is like, as I was saying, something has to be stable over time. So if you look at the distribution of the counterfactual outcome Y10, right, in the treatment arm D, you can map that into the same distribution in period 0, but then you evaluate that at the transformation of the Y1, the Y0. So basically, it's like there is a mapping between the two distributions in the two periods, but then you don't evaluate them at the same Y, but at the different Y prime and Y, but then there's a mapping between the two, basically. So that's what the approach does. So now let's talk about the quantile treatment effect and what people try to, what the paper is about here, what they're trying to achieve. So once you get the distribution, then you can, once you get the distribution, you can just compute the quantile effect here. Okay, but by just taking the difference between the quantiles evaluated at the Q. So I think this will be Q, there is a typo here. Then, so the paper kind of focused on the case where you want people who are really at the bottom or who are really at the top. So if you just use the standard approach, the AT&D base, and use the quantile regression approach, then basically your confidence intervals may not cover the true parameter, basically. That's the issue here. And then they kind of find a nice way to estimate that, and then they will cover the true effect. And it's an approach that kind of works for people that you care about in the distribution. If you care about low-income people, you probably want to look at the people at the the bottom. If you care about low birth weight, you want to look at babies at the low birth weight. So I think it's the paper makes a nice contribution. Let me show you about what they estimate, how they get the estimator, which it's new for me. So it's something that I learned from the paper. So basically, it's kind of, they look at other statistics. So let's say you have within the group, the treatment arm D, and then in period T, you look at the K plus 1 other statistics. So basically, you rank the outcome variables, okay, and you look at that, and then you compute what they call the Pareto exponent alpha TD, which is kind of the mean between the difference in the log of these other statistics. This is called the Hills estimator. And then once you do that, then you come back here. And then if you are looking at the quantile, when the quantile goes to 1, you just compute this quantity, okay? But if you are looking at the quantile, when the quantile goes to 0, it's symmetric. You compute the symmetric version of this. And once you get this, then you get the quantile effect here, okay? And you get the distribution for that, the quantile that you target, which is different from the standard one. And this is the estimator that they come up with. When I look at this, I say, wow, okay, how can I understand this? But what I kind of find interesting here, they managed to show that this estimator is still asymptotically normal, even if the rate of convergence is different. So I think that's really cool in the paper. So how do you choose whether someone is at the extreme or at the bottom or at the top, right? So what they suggest is like you do this log plot, okay, and then you start looking at where the graph becomes linear. So the points where the graph becomes linear are the points where you kind of think, you say, okay, these people at the bottom or at the top. So if you look at here, it's non-linear until from here, for me, I think it depends on each person. But then if you start from maybe 5%, 2.5%, 1%, it starts becoming linear. So this is kind of the point where you decide that, okay, these people are at the bottom of the distribution. So symmetrically for people at the top. So it's like, yes, there is some subjectivity about how you decide on whether someone is at the top or the bottom, but at least they provide this way of doing that. And I find that very cool in the paper. So then they have an application. So Hans, Miller, and Simon, they're kind of looking at the effect of earned income tax reform, right, on the birth weight of babies with low birth weight. So basically, they kind of want this, look at how this new income that they have, if the income kind of translate to they feed themselves better, that will increase the weight, okay, of the babies. So they're looking at the effect of that. And as I was saying, these people are at the bottom of the distribution. If you just plug the 18 impedance approach standard one, then you will not see the effect. The effect will be biased. And this paper actually look at the average effect. And if you look at the average effect, because they are only 2.5% or 5% in the population, you are looking at the effect on other people, not the one that you care about. So that's why I think this paper is really cool in terms of that. And most of the time, if you look at the policies, people pass, usually Congress or the legislature, they pass laws or reforms, but because they have some population in mind, the target population in mind. But usually when you just run deep in deep, you are looking at everybody else, not people that they target. So I think people should use more different changes, and more importantly, extreme changes and changes. Okay, so they're going to focus on the extreme case here, which is kind of less than 2.5%, and I think between 2.5% and 20%. So let me show you kind of the way, so this is the graph that I showed you before. Now this is the application, what they get from the application actually. So if you look at the 5% or up to 20%, you apply a 18 in-base approach, right? And then you get this. You see that actually the policy, the reform tend to increase the weight of newborns. But then if you look at now people at the bottom, this one, if you estimate, you keep going, then it will keep going up, I guess that. But then if you use the approach here, right, you kind of get the effect. It's smaller than what you will get with the 80 inverse approach. So it's kind of, they will overstate the causal effect. So here the paper is kind of showing that the causal effect is less than what you will get from 80 inverse paper. And I think it's cool, and it's in data. You don't have to code this by your own. So it's a great paper. Now I have some comments about the paper. As I said, it's a nice paper. Now the first thing, the comment that I have is, how easy is it to check the influence conditions on the application, on the given application? Because here we are looking at the tail. So sometimes the conditions are strong, and you want to give some guidance or guidelines for the applied person to say, okay, if I see this kind of conditions in my data, then I can use the approach and believe that the conditions for inference hold. So how do you do that? So in the application, I don't remember seeing that you check that. Maybe you can clarify that. So, and what does the conventional approach here does in the application? I guess that it will keep increasing, but it would be nice to show people that kind of they see the difference if it's big enough. If in the application it does make a big difference, maybe the people will say, okay, we just go with 80 and immense approach. So yes, so in practice, since you are looking at the tail, right, how many observations do we need? Like roughly, how many observations do I need in the tail to be able to use the approach? Okay, and when the outcome is discrete, right, like when the policy itself creates some bunching in the distribution, then the outcome, the potential outcome distribution that I care about is not point identified, right? So can I use the same approach there? You can partially identify the distribution, but then can the method extend to that case, right? So yes, so we have a recent paper where we kind of looking at that when the policy actually creates some bunching or some discontinuity in the distribution. You lose point identification. The 18 events approach doesn't work anymore. So can we extend the approach to that? And I think that will make it more useful. But that is for future research because this paper is already published. So everything that I'm saying is for another project. Yeah, thank you.
We got a response from you.
Let me just use the slides. I have. Yeah,
right,
I think this is perfect.
All right.
Yeah, thank you so much. I'm Yulong. I work a lot of things on extreme values like heavy tails. So I'm not expert on causal inference. So that's a fantastic presentation. I definitely know things better. I have my slides, but let me use Desiree's slides first to address some of the questions. First, how easy to check inference conditions? That's always a question that I've been asked when I present something about the tail. So for me, the key question is how should if I do this log-log plot, by the way, this log-log means for whatever IID observations, I first sort all the data, and I have a large one, the second large one, et cetera, et cetera. You take the natural log of it. So that will be the horizontal, that will be this vertical thing, vertical levels. And then also you plot it against the log of the rank, say log of 1, log of 2, log of 3. So here that means the largest observation, log of 1, which is 0 and has the highest number. Or you can do this other like switching, that's also fine. So the key idea is that if you have the underlying distribution to be a power law, a Pareto distribution, then when you take the draws from the Pareto distribution, you will see that your draw will have a perfect linear feature in this log-log plot. So that's why by eyeballing, we can see, oh, actually a lot of data would have this Pareto tail assumption. In economics, we know city size, firm size, stock returns, and there are many, many things that would have this power law. And in statistics, there's big literature to show, oh, actually, a lot of underlying distributions can be well approximated in the tail. So student T, Pareto, of course, and F distributions. Essentially, if you zoom far away in the tail, it's always going to be a power law. So in some sense, that's a parametric, like non-parametric class of assumptions. Then the question is, where should I think about the tail, right? You couldn't approximate the whole distribution as the Pareto. for example, student T has a right symmetric thing. You only look at the very tail part. That means if I do the log plot, when I see something that's roughly straight line, I believe this is a good approximation. So we can think this choice as a tuning parameter, like choosing the bandwidth in kernel estimations. And then depending on what the true distribution is, how close is it to the Pareto distribution, you can choose to be very conservative. If the whole distribution is Pareto, you will use all the data set. If you use student T, which is quite different from Pareto, it's only similar to Pareto in the very tail, then roughly using like 2% or 1% is typically the right way to go, and depending on the sample size. So that's one thing. And second, how to define your tail depends on your sample size. If you have 100 observations, maybe top 10% is extreme. If you have 1 million observations, maybe you can use, I don't know, the top 1,000, and that's also extreme. So that's like data-dependent thing. And then there are statistic tests about this thing. You can use kernel growth Skolmer's test or other tests to have a formal diagnostic thing, whether that's exactly straight line or not. So we're just trying to be user-friendly, so we didn't propose that in the paper, but there was a lot of things to do. And then the second question, how does the conventional CIC go? We also have the plot, but we just suppress that from the paper. And that will go up as we predicted. And then the most important question is the confidence interval going to be really, really wide, as you can imagine. Because they're not, right, the denominator goes to 0, so their confidence interval is infinitely wide. So that's why doing inference is like a big gain when we use the Pareto thing. So essentially, if I go to the Pareto thing in the tail, I know Pareto is fully characterized by just the tail index, like how fast the distribution decays to 0. So I'm going back to a parametric family. I just need to estimate one parameter, alpha, how heavy the tail is. So that's why I can use relatively small sample size, which I get in the tail, to estimate just one parameter, and then trace back the whole distribution, because I know that's Pareto. So that's essentially what we do. And then question, how many observations? So based on my experience, we need the tail to have at least 100, 150 observations. So if you think about top 3%, that means you need in total 5,000 or more to make sense that estimator. Or if you have only 100 observations, I'm sorry, you can't do things about the tail. You just do averages for. And then I don't have the exact answer for these two things, but I have my partial answer, something I've been working on. Stop sharing. Right.
Really, maybe we'll just see.
Okay. Yeah. 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 So I don't have the exact answer in the causal inference setup, but I do have something that I'm working on when the outcome is discrete. So y is 0, 1, not the causal like potential outcome setup. Suppose you look at this traditional binary choice model, like you have y equals 0, 1, x is a continuous random variable, and then suppose I'm doing estimation of this. I'm doing this conditional estimation of the probability y equals 1 given x, but now x takes extreme values. X is super hot whether people get sick or not, something like that. And I know this probability should be quite close to 0 or 1, or some other like extreme probabilities. And if you use a loaded or probit model to estimate this, it's going to be terrible because in the tail, right, that's definitely not concave or convex. You can't use normal assumption. That's good in the middle, but not in the tail. So how should I do inference about this? Or the derivative of this, like partial derivative of this, I can easily switch the condition and the target by using the Bayesian, right? By Bayesian thing, you can easily, this is just exactly true, that you have the density of the x, and then the density of the x equals to conditional y to 1, conditional y to 0, but now let x goes to infinity. And you know x has continuous random variables, and then it has Pareto tail. You have essentially two Pareto thing density in the tail. You just need to estimate the two Pareto index using the data of x given y to 1 and given y to 0. Combine pieces together, and that would give a very good inference. That's one thing. Second, how about I have like functioning, like mixed thing? I don't have that in the causal inference either, but I do know suppose you have y, which is combination, but it's A plus B or A plus B plus C, so it's like combination of different or mixture distributions. I don't want to make an assumption that A is whatever distribution, B is whatever distribution, but if I'm interested in the tail of, say, Y, or A specifically, I know that the tail, say the right tail of the Y, would be dominated by either A or B, whose tail is heavier. So we think that in a summation of student T and the Gaussian, in the middle you can't tell the difference. But in the tail, you know the extreme values are all coming from student T, but not normal. Then think this as a student's performance, and then A will be the school effect, B will be individual effect, and there might be C, some random noise, etc., etc. And then I don't want to make any assumptions, but actually, if I look at the very top thing, they may come from either the very top school effect or the top student effect. So I can estimate the tail of the Y, and that refers to the tail of either student or school. And then if I have multi-dimensional data set, like 2 pairs, many schools, many students, I can take average, et cetera, the difference, so I can figure out those tail index by themselves and compare which one is heavier. That's what do we have. Thanks.
So we've got a couple minutes for questions.
Thank you. So just a small question about dimensionality of unobserved heterogeneities that you have in your structural model for the potential outcome that Desiree mentioned should be scalar.
Yeah.
Right. And I'm just wondering, I guess I just don't know changes and changes well enough. Can't you just, so if the potential outcome is scalar, isn't that just, the scalar quadratic representation or whatever you want to call it, the usual, you express a continuous random variable through a uniform scalar random variable, or is that something substantial? That's probably a stupid question.
No.
Yeah, but
so this is not our assumption. This is the whole thing, like extreme CIC make those assumptions. So we're just user of that. So the reason is that, well, you have to have a scalar so that this inversion will, like the CDF, the inverse of CDF will be well defined. Otherwise, you can't do inverse. That was just the only purpose. And yeah, instead of like, if I have multiple things, it's going to take the averages like for all those elements, but if you have like multiple covariates, you can't take like the joint CDF and inverse, et cetera. So that was just my understanding.
Yeah, but I would say that suppose that my weight depends on my productivity and also depends on my motivation, right? So these two variables are not observable, right? So if it's a choice or outcome that depends on 2 or multiple unobserved heterogeneity, then you cannot use this method. But then technically, in statistics, if you know that the distribution is continuous in swiftly increasing, then you can always write it as a function of the quantile inverse, like you're saying. Yeah. But then it's like mechanical, it's statistic. And then if you come to economics, you may not, this U that we have may not have economic interpretation. Yeah.
I might have to get sure.
Just step back a little bit. Yeah, cool. So this is a question about changes and changes. I recognize like your guys' value added is doing changes and changes with like the tail distribution. So okay. Basically, so Desiree, you had a cool slide that like showed how like parallel trends would just be a stronger assumption than like the assumptions required for identification for the changes and changes estimator. I guess what I'm trying to work out in my head, and I'm wondering if you guys have done this because you know this literature, like is like the classic parallel trends graph that you see in every applied paper is like 2 lines side by side. Like like, what's like the under the changes and changes estimator? Can I get like crisscrosses? Like how crazy can we get here?
So yeah, can I just?
Yeah.
I think it's not your thing to.
Please.
So this is a good question. So basically, if you look at, I mean, when I was taking my first or second year PhD, they draw this line for parallel train.
Yeah.
But basically, you only have two data points, right? You have period 0 and period 1. What happens between, it doesn't matter. You just need this difference between the treatment and control group in period 0 to be the same in period 1. Then in between, anything can happen. So the standard parallel trend assumption, they used to draw this line to show that it's about trend, right?
Yeah.
But as you're saying, you can have some periodicity between,
Oh, I got it.
and then it goes up, it goes down, and then it reaches the same point at the end.
So I could have a straight line and
Yeah,
it's crossed.
and it cross. But as long as you get the same difference in period 0 and period 1, you're fine.
Yeah, I got it now.
So that's why I think the terminology parallel trend can be misleading. It's just the bias stability, right? The bias equality between period 0 and period 1.
Yeah.
The selection best has to be missing.
No, that is really weaker. Yeah, I got it now.
So I'm struggling to sort of tie the notion of the conditional quantiles to the extremes of the unconditional distribution that you're using, right? If I understand. So the AT those are conditional quantiles. And yet when I look at sort of the biggest value or the smallest value in the data set for the outcome, that's sort of not conditional on the covariates, right? So that overlap, kind of, it's almost like the right-hand side picture was about the conditional quantiles or the quantiles of U, really, right? And then all of a sudden I've switched to the unconditional ones.
No, that's.
Or maybe not, yeah.
Maybe, so we're
Yeah.
in terms of that conditional, unconditional thing, we're exactly using IMBIS and AT. So for covariates, as far as the standard method or the extreme value version of that, you first have to run whatever regression to get the residue. So for all the axes, they're already gone. And that's also like the IMBIS thing, right? They only have the CDF, the Y part, conditional on your traded or not traded, or conditional on your period 1 or period 2 with 0. So there's like no X in their frameworks either. And then for us, yes, you do the estimation first. And then in the published version, we show actually if you do estimation, it doesn't really matter, because when you have the estimation, if you believe the estimator, the beta coefficient is root n consistent, because the convergence rate of the extreme values is typically slower, like the non-parametric rate, you're in the tail. So the first data estimation will not make any effect there because converges faster. So that's one benefit. And second, in terms of conditional on being traded or untraded, yes, you split the sample first. You get period 1 traded, take those order statistics in that subsample. And then period 0 untraded, or so they're like 2 by 2 cells. You take the extreme values in all those 4 cells and do this. Yeah.
All right, thank you.
All set?
So, real quick, I just wanted to acknowledge.
Real quick, I want to acknowledge a couple student helpers from the econ department. Daniel Cho will be on the market soon. And Jack Chappell is on the market. Jack, 5 words or less, what's your job market paper about?
It's about social interactions and how they influence people's take-up of medication.
And I'd add that Jack has a just published health affairs piece on the health of middle-class Americans. He's the first author. It's getting a ton of attention. Check it out. Thank you.
So we'll be back at 10:30 for the extremes in the tails of AD. So